Hello, I'm Tom Nahumi from DELL EMC, and today I'm going to show you a demonstration of DELL EMC XtremIO X2 Container Storage Interface plugin for Kubernetes persistent storage applications. As you can see on the screen, I have a 4-node Kubernetes cluster. I installed the XtremIO CSI plugin on all 4 Kubernetes nodes, while the nodes are running the node role and one of them is also running the controller node. Currently, the Kubernetes cluster is empty, no pods or volumes are deployed yet. Under Storage Classes tab, we can find the predefined XtremIO storage classes, the default one, as well as the high, medium, and low, which are based on XtremIO quality of service policies and configured to consume storage from the XtremIO cluster. By editing the default storage class, we can see that the provisioner is set to XtremIO CSI plugin, reclamation policy is set to delete, and the volume binding is set to immediate. Now, let's take a look at my XtremIO cluster. In order to demonstrate the plugin capabilities, I deployed a multi-cluster with 2 XtremIO X2 X bricks with different capacity. Both are managed by the same XMS. For the purpose of this demo, I chose to deploy Yugabyte Database. Yugabyte Database is the open-source transactional high-performance database for building internet-scale globally distributed applications. Yugabyte Database is comprised of 2 types of distribution services, master and tablet containers. In the Yugabyte YAML file, I set a volume claim template for each of them to consume storage from the XtremIO cluster via the CSI plugin, and it basically means that for every new pods, a new 200 GB volume will be created, mapped to the relevant Kubernetes node, mounted and formatted with a file system. Now, I'm creating the Yugabyte application with kubectl command. The default application deploys 3 master and 3 tablet nodes. As you can see, the pods are being created as well as their persistent volumes. During this process, the volumes are being created on the XtremIO cluster, mapped to the relevant Kubernetes node, mounted and formatted with a file system. By navigating to the XMS, we can see that the volumes are being created at the XtremIO level as well. By default, when there is more than one X brick under the same XMS, the CSI plugin creates the volume on the cluster with more free capacity, in order to load balance the capacity between the X bricks. We can, of course, create a new Kubernetes storage class and set it to consume volumes from a specific X brick by specifying the cluster ID as a parameter in the YAML file. Now that the deployment completed, I am navigating to the Yugabyte user interface using the service IP. Here we can see the different objects and configurations of the Yugabyte application. We'll come back to this later on after generating some loads on this cluster. Now, in order to demonstrate the XtremIO unique performance capabilities, we will run a simple key value workload against our running Yugabyte cluster, which is residing on multiple XtremIO X2 LANs. Each represent a persistent volume which is bounded to a single container. The application writes out unique string keys, each with a string value. There are multiple readers and writers that insert, update, and read these keys in parallel. From the XMS, we can see the performance of those pods and persistent volumes, while the load is distributed across all nodes in the cluster. As I mentioned, the default stateful set creates 6 pods. Now, let's scale up the worker stateful set and create 7 more replicas. As you can see, the pods are being created instantaneously as well as their XtremIO persistent volumes within seconds, allowing the customers to scale up and increase performance to fit the business agility needs. Exactly the same way, we can scale down the cluster and reduce the number of pods when they are no longer needed. The pods will be destroyed and the volume will be unmapped and ready for deletion. Another interesting feature is the ability to automatically apply XtremIO quality of service policies on Kubernetes persistent volumes upon creation. Integrating QoS policy with Kubernetes storage classes allows the customer to guarantee service for critical application and production copies, limit noisy neighbors, and provide multi-tenancy. During the CSI plugin installation, 3 additional storage classes were created: high, medium, and low, and their corresponding QoS policies at the XMS level. By editing the storage class, we can see that there is a QoS policy ID which is assigned to this specific storage class. By navigating to the XMS, we can see that those QoS policies were created at the XMS level with 15, 1, or 5 MB per second per gigabyte. Of course, these policies can be edited and new policies can be created to fit the customer's specific needs. Now, let's go back to the CLI and delete the application I previously created and its persistent volumes using the kubectl delete command. Now, I'm editing the stateful YAML set file, and instead of using the default storage class, I'm setting the master stateful set to use the high storage class and the worker stateful set to use the low storage class, and then I'm saving the file. Now that our application is deleted, let's recreate it with kubectl command, now with the new storage classes instead of the default ones. Within a few seconds, we can see that our pods are ready and their persistent volumes are running by running the kubectl get pods and kubectl get pvc commands. We can see that the new persistent volume claims are associated with high and low storage classes and of course the corresponding persistent volumes. From the XMS, we can see that the new volumes have quality of service policies assigned. Now, let's rerun the key value workload against our running Yugabyte cluster and connect to the Yugabyte web interface using the service IP. On this page, we can see the 3 tablet containers. We can see that the write operation per second are increasing. By navigating to the XMS, we can see that the bandwidth is limited by the QoS policy. The green dots to the right of the volume name indicate that QoS is applied to that specific volume. XMS delivers an HTML5 user interface, allowing the customers to monitor, manage, and optimize storage health to ensure performance of Kubernetes applications. The following report is showing the block size distribution during the sampled application run. We can see that most of the bandwidth used is 64 kilobyte blocks, as these are the block sizes that were configured at the application level Yuga by database to use against our storage array. We can also see the performance in a block size granularity for each and every block size that were in use. The following reports are showing I/O per second and bandwidth of the sample application run, providing with the storage administrator the ability to identify the characteristic of the I/O patterns and his Kubernetes applications. I hope you will find this demo useful, and thank you very much for watching.